Hello guys, and welcome to another calculus video. In this video we're going to be talking about different ways of approximating the gamma function. So the first method that we're going to use is just a direct Taylor series, which is your classic approximation. And then we're going to be using a Taylor series in Digamma, which is going to be pretty similar, but we're going to get a bit of a different expression. And finally we're going to use what's called the Laplace's method, I suppose. This is Laplace on the left here. I just thought I'd put a picture of him in order to approximate and discover, we're going to rederive Stirling's approximation. And all three of these approximations are going to have their own times when you're going to want to use them. They'll have their pros and their cons, so we're going to talk about those two at the end. So let's jump right into it. So the first approximation we're going to do is just a Taylor series. So for that, we're going to need to know a lot of different values of the gamma function and its derivatives. So first, we're going to center our Taylor series at 1. And the reason we're centering it as 1 is because we can't do a Maclaurin series around 0 because the gamma function just diverges there. So that's not going to help us. So we're going to have gamma of 1 is equal to 1, of course. Gamma prime of 1 is going to be the integral from 0 to infinity of t to the x minus 1 e to the negative t. We're going to take the partial derivative with respect to, or we're going to take the derivative with respect to x, right? And so we're going to end up just having an ln x in here, or ln t, sorry. And this is a super famous integral. If we go ahead and just set x equal to 1, we're just going to get this, and this is just equal to negative gamma. So gamma prime of 1 is going to be nothing but negative gamma. And then we're going to also find the second derivative and the third derivative. So second derivative is going to be gamma double prime of 1. The way we're going to calculate this is using the digamma function. So we know that digamma of x is equal to gamma prime of x over gamma of x. So the first derivative, I'm just going to write digamma prime of x. You could also write it as digamma with little 1 there of x. It's going to equal second derivative over gamma of x, and then we're also going to have minus digamma of x squared. And so if we want to solve for gamma double prime of 1, we can just plug everything in. Digamma 1 of 1 is going to be nothing but the sum from n equals 0 to infinity of 1 over n plus 1 squared, just differentiating the original digamma function. So just a reminder, digamma of x equals negative gamma plus the sum from n equals 0 to infinity, 1 over n plus 1 minus 1 over n plus x. So we're just differentiating that, so this is equal to pi squared over 6. So if we go ahead and plug that all in, we're going to get pi squared over 6 equals gamma double prime of 1 minus gamma squared, or gamma double prime of 1 equals gamma squared plus pi squared over 6. So we can go ahead and plug that in over here. And for gamma triple prime of 1, I'm actually going to just go ahead and write out the answer because this is something I derived in a previous video. It's actually one of the very first videos on my channel. You can go check it out. It's the integral from 0 to infinity of e to the negative x times ln cubed of x. And so gamma triple prime of 1 is going to equal negative 2 zeta of 3 minus gamma cubed minus gamma pi squared over 2. All right, so now that we have all that, let's go ahead and write out our Taylor series. So we are going to write that gamma of x is approximately equal to 1, and then we're going to be subtracting gamma times x minus 1, and then adding gamma squared plus pi squared over 6. Actually, I'll do that on the next line because there's not really space here. X minus 1 squared over 2, and then minus 2 zeta of 3 plus gamma cubed plus pi squared gamma over 2, and this is all times x minus 1 cubed over 6. So this is our first approximation here. Sorry, it's kind of lengthy, and that's part of the reason why this approximation might not be the best option. So there is a lot of terms in there, and so if we wanted to actually expand the approximation and add more terms, as you can see, they would just keep getting more and more complicated. So that's one of the downsides to the Taylor series. But the Taylor series is super simple and easy to understand and to use, and it's easy to also expand into the complex plane. So I have a graph here of this approximation. The orange curve is the actual gamma function, and the blue curve is our approximation. Now remember, this is just a third order Taylor series, so it doesn't exactly match up very well. But you can see that in this region from about, I guess this is like 0.4 to about, I don't know, 1.2-ish. It's actually a very good approximation, and this pink graph over here measures the error, so this would be gamma of x minus our approximation of gamma of x, right? And so you can see that we have actually a very, very small error within this region right here, and so it's actually going to be a pretty useful approximation. Now obviously, because it's a Taylor series and we have an asymptote at x equals 0, that means our radius of convergence is always going to be less than 1. So that means we're never going to be able to approximate any values greater than gamma of 2. However, because of the properties of the gamma function, as long as we have a region like 1 unit long, we can use the gamma functional equation, which is x gamma of x equals gamma of x plus 1, and we can kind of just use this to extrapolate other values of the gamma function and cover the entire plane. So overall, a pretty solid option. With only 3 terms, we have pretty accurate approximation, but there are definitely better options for certain situations. So let's go ahead and look at another example. So a slightly better behaved function than the gamma function is the digamma function. And so digamma of x is equal to negative gamma plus the sum from n equals 0 to infinity of 1 over n plus 1 minus 1 over n plus x. Okay, and the reason we're using the digamma function is because, as I stated before, digamma of x is equal to gamma prime of x over gamma of x, which is equal to the derivative of the natural log of the gamma function. So if we can create an expression for gamma of x, we can also, for digamma of x, we can also create an equivalent expression, just integrating it and raising e to the power of it, and we can get gamma of x. So let's go ahead and write a Taylor series for digamma of x. So digamma of 1, again, we're going to have to work around 1 because at 0 we have asymptotes and that doesn't really help us. Digamma of 1 is clearly just negative gamma. Digamma prime of 1 is just going to be the derivative. So if I just go ahead and find this, this is just going to be the sum from n equals 0 to infinity of 1 over n plus 1 squared, which is just pi squared over 6. Digamma double prime of 1, we're just going to go ahead and again, you can replace these primes with numbers corresponding with the correct polygamma function, but I'm just using that notation because it's going to be more useful to us. Just differentiating this, we're going to get the sum from n equals 0 to infinity of negative 2 over n plus 1 cubed. So we're just going to have negative 2 zeta of 3. And we can just go ahead and keep going if we want, since these are actually super easy to evaluate. So that's another advantage to using the digamma function instead, because its successive derivatives are just equal to values of the zeta function. So here we're going to just get 6 times pi to the 4th over 90. So if we go ahead and write this all out, we're going to get that digamma of x is approximately equal to negative gamma plus pi squared over 6 x minus 1 minus zeta of 3 x minus 1 squared plus pi to the 4th over 90 x minus 1 to the 3rd power, right? All right, and all we have to do is go ahead and integrate this. So when we integrate this, we're going to find that natural log of gamma of x is going to be approximately negative gamma x. And we don't have to worry about that constant term because we're centered around 1, right? So when we plug in x equals 1 on both sides, we're going to get natural log of gamma of 1, which is just 0, and all these x terms will also cancel out. So we don't need a constant term in here. Then we're going to add pi squared over 12 x minus 1 squared minus zeta 3 over 3 x minus 1 cubed plus pi to the 4th over 360 x minus 1 to the 4th power. And I'm just going to go ahead and write this as this. And in order to solve for gamma of x, you could just raise both sides to the e power. And we're going to take a look at how this approximation looks. So I have the graphs here. And you can see that this one behaves a lot nicer for a bigger region, of course. It still does not act very nice as we approach x equals 2, but it gets a lot closer, and we can tell that if we kept adding more terms, we could hopefully get a much better radius of convergence in that situation. So we could definitely get a more accurate approximation, and the great thing is, since the derivatives of the digamma function match up with the zeta function, it wouldn't be too hard to calculate its successive derivatives and add more terms. Also, since we're raising e to the power of the function, this function is a little bit better behaved in general, probably easier to differentiate and mess with in that way. So this approximation is a little bit better. That also is because we added more terms in this case, but it would be a lot easier to add more terms and get an even better approximation. So that's definitely a reason why you would want to use this formula. And finally, we're going to look at the Laplace method, or Stirling's approximation. So this is going to be a little bit of a more complicated derivation. So first, we're going to start with gamma of x equals integral from 0 to infinity of t to the x minus 1, e to the negative t dt. So this means that n factorial is going to be n factorial is going to be equal to the integral from 0 to infinity of t to the n, e to the negative t dt. So now we're just going to go ahead and make a bunch of substitutions and reorganize this integral. First, we're going to let t equal n times x, which is going to be our dummy variable in this case. So we're going to have n factorial equals the integral from 0 to infinity of n to the n, x to the n, e to the negative t, or I guess e to the negative nx. And then we're going to be multiplying by n dx. So if we go ahead and reorganize, we're going to have n factorial equals n to the n plus 1, integral from 0 to infinity of x to the n, e to the negative nx. Next, we're going to combine this all into one big exponential. So instead of we're going to have e to the negative nx, right? And then we're also going to have plus n ln x. And that's going to give us the same thing that we had before, dx. Now we're going to reorganize this one more time in the top here, and we're just going to write this as e to the n times ln x minus x, right? And now we're going to do a little bit of a tricky substitution here. We're going to analyze ln x minus x. We're going to write out its second order Taylor series. So first, its value about 1 is just going to be negative 1. The first derivative is 1 over x minus 1, so evaluated at 1, that's going to go to 0. And the second derivative is negative 1 over x squared. So that's going to just be negative x minus 1 squared over 2. And we're going to ignore all the terms after that. And the reason we're saying we can ignore all these other terms is because once those higher order terms, quote unquote, kick in, we're assuming that n is going to be a very large number. This is an asymptotic approximation. And so once we assume n is a very large number, once these higher terms kick in, we're already going to have a very large number in the exponent of e. And so that's going to give us a very, very small number that won't actually contribute very much to the integrand. So we're just going to go ahead and replace this right in the integral. We're going to have -1 minus x minus 1 squared over 2. Next, we're just going to bring out this e to the negative n. All right, and we're left with this wonky integral right here. So this looks like a Gaussian integral, and that's in fact what it is, but unfortunately it's going to be a little bit awkward for us to evaluate. So if I go ahead and just shift it over by 1, we're going to be integrating from -1 to infinity, and this is going to be e to the negative n x squared over 2. All right, now we're all ready to evaluate this integral. The problem is we're starting at -1, so this and that's not 0 or negative infinity, and so it's kind of hard to evaluate this integral. So we're going to use Laplace's method, which basically says that according at least to our approximations that we've made, if n is super large, our Gaussian is going to look something like this, right? So already a Gaussian looks something like this. But if n is very large, then once x reaches even a very small number, it's going to quickly curve down. So our Gaussian is going to look something more like this. It's going to start at the same point at x equals 0, but then it's going to sharply curve down, and then it's going to hit the bottom. And as n becomes super large, it's going to approach all the way downwards like this, and essentially become nothingness, right? And so the importance of this approximation is basically what we're saying, all the area that's accumulated under this curve, right? All of it is essentially right at the center between -1 and 1, or between any small number and any small negative number and its positive version, right? So we can actually rewrite this, and assuming our approximations are correct, as the integral from -infinity to infinity. And this is super easy to evaluate. After some u substitution, you're going to find this is just equal to square root pi, right? And then you're just going to divide by square root 2 over n, right? And so once we reorganize this completely, we're going to get n factorial is approximately equal to square root 2 pi n over e to the n. And so this is our approximation for the gamma function. We just have to shift it over by 1. So let's go ahead and look at what this approximation looks like. So this is our Stirling's approximation. You can see that when we have small values of x or n, it just doesn't work at all. And that's why we need to assume that we have large values of we have a large value of x. But as you can see, afterwards, it pretty sharply attaches on, and I didn't show the whole graph because I'm kind of trying to show the whole area, but it very quickly achieves a very similar value. This error graph is actually a little bit different than it was before. Before we had gamma of x minus our approximation of gamma of x. In this case, it's gamma of x over our approximation of gamma of x minus 1. Or maybe it's actually the other way around. But anyway, it's kind of showing that although it doesn't exactly attain the correct value, the value is multiplicatively very, very close to the actual value of the gamma function. And so that makes it very helpful because we can just pick a very, very large n, use Stirling's approximation, and then use the gamma function functional equation in order to move back to more normal numbers. So, in essence, I want to talk about when we want to use all of these different approximations and why some of them have pros and cons. So, for this first one, our pros, it's simple, it's easy to calculate, and it's good for computers because there's almost no computation required to do here. right? It's just a simple polynomial. You plug in the coefficients, and a calculator, you can do that with a normal calculator. You can do that by hand even if you have enough time. It's definitely the most straightforward way to approximate the gamma function. You don't have to do any integrals or any stuff like that. All you have to do is plug in this equation, and it's super easy. You know, we have a good range of values that we can pick from here, and then we can use the gamma of x equals x gamma of x equals gamma of x plus 1 in order to attain other values of the gamma function. So overall, a pretty good option. However, it is a relatively poor approximation. And so that's not going to be the best option if you need a super accurate value, because it's actually pretty hard to add on more terms. Now for this next one, the pros would probably be it's easy to expand, easy to add more terms. So that means we're going to be able to add a lot of terms and get a great approximation super easily. So this is more of a good approximation, right? However, one con is it's harder for you to can't evaluate it by hand, right? Because we have that e to the x in there. So if we wanted to evaluate it by hand, we would need to use another power series, and it just wouldn't be efficient. It's also going to be a little bit more difficult for a computer to actually calculate those values. And for our last value, our last one, Stirling's approximation, it's a more or less, it's an okay approximation, I'd say. It's pretty good. It doesn't actually come super close to the actual value of the gamma function. There's like, if you subtract the two, there's a relatively large difference, but it's much better than these other approximations because it's good for large numbers. And what you can actually do is you can pick a large number and then use the gamma of x equals gamma x plus 1. And just use it repeatedly to get gamma of a small number. So for example, I could calculate with this gamma of like 27 or something, and then just repeatedly divide back until I can get gamma, or I guess 27.3 would be more useful to us, right? I could just repeatedly divide back to get gamma of 0.3. So overall, these three approximations have their pros and their cons. I would say my favorite is probably the one in the middle because it's the easiest one to get really high accuracy really quickly. But if I'm ever doing anything by hand and I don't have access to a calculator, I'm definitely going with the first option. Stirling's approximation, in my opinion, is not very good for casual maths. It might be good if you have like a NASA supercomputer and you're calculating something like that. I don't know. But then you could probably just run the integral. But it is useful sometimes to use Stirling's approximation in certain integrals and differential equations, stuff like that, infinite sums. So it definitely has its merits as well. So overall, I hope you guys enjoyed the video. It ran a lot longer than I expected, but I think, you know, it was a lot of fun. We learned a lot about power series and about approximations, and now you guys have a few tricks up your sleeve if you ever need to approximate some non-elementary function, you know, by hand or with a computer in the most efficient way possible. So yeah, hope you guys enjoyed the video, and I'll see you next time.